Thank you. Good morning, everyone, and welcome to the 28th Annual Glaucoma Foundation Think Tank meeting, a patient-centric approach while incorporating the latest science. As you heard Bob said, we were trying to bring in different subspecialties into this field and to address this really complex disease. And I would argue now that there's a lot of mature scientific specialties, and we need to sort of synthesize this information in a way that we can help the patients. And we have a new set of experts that we're bringing in, which are the patients. We need to hear from them. This is the organizing committee. I want to particularly thank Greg Harmon, whose unassuming leadership has really helped the foundation to thrive, and Bob Weinrab, who spent a lot of time with me sort of synthesizing this program. Here's a point I want to make and why we're running the meeting the way we're running it. When I graduated from my fellowship in 1992, if you put glaucoma as a keyword and put it into PubMed, there were 842 papers. In 2022, you do the same thing, and there's close to 4,700 papers. And while we have assembled the world's experts in this room to talk about some of the latest developments and synthesizing some of the latest findings in glaucoma, I could guarantee you we're all going to learn from one another, and we're going to learn from the patients. And that's what's really exciting. And what we really want to do with this meeting is to have discussions centered around 6 different topics that you see here. We're going to have talks that sort of build on one another. I'll leave it up to the moderators, but the idea is to let the people talk and to have the discussions at the end of each session. If there's a burning question that you want to hear an answer to at the end, immediately after a talk, we can entertain 1 or 2 of those. But what I would recommend that you all do is to write your questions down and try to reserve them for the end. There'll be plenty of time to talk. You know, we want to try to generate a white paper from this meeting, and here are the deliverables. We want to see if, after listening to all these talks, if we can come up with novel strategies that prevent glaucoma, stabilize glaucoma, and recover vision loss from glaucoma. These are the things that we think that with these 4,700 papers, and notice that if I go back, the knowledge in glaucoma isn't increasing linearly, it's increasing exponentially. And so we really want to leverage that and to help our patients. That's the goal here. Okay, so with that said, we will get going. I'm moderating the first session, and this first session is on glaucoma data integration. And what you're going to hear about for the next hour and 20 minutes is how big data is impacting our understanding of glaucoma. And our first speaker is going to be Sally Baxter, and she's going to give us an overview of databases available to advance our glaucoma knowledge. Let me just say a few words about Sally. She's Assistant Professor, Division Chief of Ophthalmology, Informatics, and Data Science at University of California, San Diego, Shiley Eye Institute. She's a physician and an informaticist who integrates comprehensive ophthalmic care with research investigation into big data, artificial intelligence, and health information technology systems. She's the first ophthalmologist to receive the NIH Office of Directors Early Independence Award and was recognized in ophthalmology management's 40 under 40. I guess we know how old you might be. She's a chief of the Division of Ophthalmology, Informatics, and Data Science at University of California, San Diego, chair of Data Standards Work Group of the American Academy of Ophthalmology, member of the AAO Committee on Artificial Intelligence, and co-lead of the Observational Health Data Science and Informatics Work Group in Eye Care and Vision Research. He's a PI of multiple grant-funded research studies and has authored over 75 publications, which is really impressive. She's double boarded in ophthalmology and clinical informatics, and she's literally traveled around the world to be here with us this morning, and we are really thankful that we have good air and we could all breathe, and we have this wonderful venue, and we have all these people online who are also interested hearing us and will be participating in the discussions that we have today. So if we can give Dr. Baxter her slides, and I will turn the podium over to her.
Thank you so much for that kind introduction, and thank you to the Glaucoma Foundation for letting me join the meeting and give this talk. Are the slides up or? While we wait for the slides, what Lou was referring to is I am temporarily based in Japan, since my husband is active duty Navy and the US military, and so it's great that everything worked out for me to be able to come here, especially with the recent weather. All right. So these are my disclosures, and again, very special thank you to the Glaucoma Foundation for supporting some of my research work. So just an overview of what I'll be talking about today. It's a short 10-minute talk, but I will try to briefly provide information about some databases that are available for advancing glaucoma knowledge. Of course, this is not an exhaustive list, but just an overview of some databases, including some more recent ones that you may not necessarily be aware about. For each database, I'm going to go over some of the research studies that have used these data sources. And for some of the researchers in the room, if you're interested in gaining access to these data for your own research, I'll go over a little bit of that. And finally, a little portion on understanding the importance of data standardization, particularly for glaucoma. So there are several different types of sort of big data that we talk about. One is, using data secondarily that's generated from routine clinical care, and another are, data that's sort of prospectively generated in research studies. For today's talk, I'll primarily cover the first category. And just as an overview for all of these data in general, what are some of the benefits of using these real-world databases? I think one key aspect is understanding real-world practice patterns and outcomes. When we look at practice and routine care data, things don't always happen the way they do in a controlled research study. So it's important to understand how clinical care is being delivered and what the outcomes are for patients in different practice settings. When you have databases that bring in data from different places, that is really helpful for increasing sample size and statistical power versus individual siloed data sets. So that's really another key advantage of these databases to enhance the rigor, and also in some cases for studying rare disease, this can really be a benefit. Certainly combining multiple data types. So traditionally you might have databases that are solely focused on ophthalmic data, but as we are increasingly aware of, there are different connections between eye disease and systemic disease. And certainly in today's conference, we'll hear many other speakers talking about those connections and how do you really study those without having those different types of data available. So I think databases can really offer an advantage there as well. And again, in recent years, we've come to really understand the importance of diversity, and diverse representation is really facilitated by these databases that bring together diverse data sets for both patients and researchers. So some of these databases allow wider access to data, not just from researchers at R1 universities, but people in community organizations or even patients themselves. So just to start, at the most granular level, you have local or institutional data warehouses, and typically this is electronic health record or EHR data maintained at individual institutions. One benefit is that it often includes systemic data as well, but then a drawback is it may have limited generalizability if you're only looking at a single site. However, these can inform local interventions like quality improvement initiatives and so forth. So if you look at some of the research studies that have been done on this, these are examples of a few papers that have looked at individual institutional EHR data for understanding ophthalmology visit utilization and missed visits, gaps in adherence to follow-up, which we all know is very important in glaucoma. And then actually, Josh is here. One of his papers I found was looking at text parsing and using information from the EHR to understand medication adherence at his institution. So access to data can really vary depending on your institutional policies. Sometimes you can have user-facing tools for quick exports and queries, but oftentimes for larger scale data extraction, you have to go through centralized services, often through your CTSA entity. Now, shifting gears a little bit more to national level databases, one of the most well-known ones is the AAO IRIS registry. It's actually now considered the largest medical specialty database in the world, and you can see the growth over time in this figure. Estimates right now are that there are 70% of US ophthalmologists contributing to this database. One drawback is it does not include much in the way of systemic or non-ophthalmic data. But for the ophthalmic data, there are a huge number of visits and representation of a large array of practice settings. And again, for studies that are relevant to glaucoma, many studies have used the IRIS registry to be able to look at, for example, MIGS utilization patterns, variations in practice patterns between academic and non-academic settings, risk factors for drainage device revision or removal. So this database has been used in many ways to look at real-world patterns and outcomes for glaucoma care. Currently, access is mostly limited to an analytic center consortium of a couple of academic medical centers, but there are research awards that also enable access to the IRIS registry, including through the American Glaucoma Society. Another national database that I've had the pleasure of working with personally is the NIH All of Us Research Program. And this is really a prospective cohort study that's emphasis on diverse enrollment and obtaining data from participants who have been traditionally underrepresented in large-scale population-based studies. And it's a similar model to the UK Biobank and the VA Million Veterans Program, which I unfortunately won't have time to talk in detail about those, but I know Anthony is going to be talking about some work with the UK Biobank. But this is a database that not only has EHR data, but also survey data, physical measurements, wearable data, and biospecimens to enable genomic analyses. These are some of the stats around the current enrollment, and I just wanted to highlight that over 50% of the database is consistent of participants from racial and ethnic minority groups. And if you have a broader definition of underrepresentation, including income, education level, disability, and so forth, over 80% come from groups that are underrepresented in biomedical research. And so now this resource is available. We've been able to do several studies using it for glaucoma, including AI and ML models, looking at healthcare disparities, visit adherence, medication adherence, and others have looked at interactions between blood pressure and blood pressure medications with glaucoma. So it really is a rich resource for glaucoma research. One of the great advantages of this database also is that it has fairly easy access. One of their guiding principles was democratizing access to data. And so really anyone with an internet connection can go on to researchallofus.org, look at the data browser, and there are really minimal barriers to accessing the data and analytic tools. You do have to have a data use agreement in place with your institution and the All of Us program, and you do have to do responsible conduct of research training, but you can essentially gain access to the database within a couple of hours. Since I was one of the early users, I actually was able to help with some of their promotional materials, and so there are resources online if you want to learn more about the database. This is probably the only thing that will ever reach 1 million views for me, and that is mostly a testament to their huge PR marketing team. Another national data set that is very ophthalmology focused that I wanted to highlight is the SOURCE Consortium, and the PI for that is Josh Stein from University of Michigan. This is a consortium of EHR data from academic ophthalmology departments using EPIC across the US. And similar to All of Us, there are a wide range of data types, ophthalmic data and systemic data. One thing that the SOURCE Consortium has that All of Us does not is inclusion of some free text notes, and there are some sites contributing imaging or testing data, which I think is very helpful for glaucoma research. Several studies have been done using SOURCE, including work around phenotyping for pseudoexfoliation, for example, and looking at triaging patients with glaucoma and clinic visits during COVID-19 pandemic. So again, a really rich resource for looking at novel associations and real-world outcomes. In order to access this data, you do need to be a contributing member of the consortium, have a clinical champion or site lead. And if you're interested, I would encourage you to talk to Josh about joining the consortium. So in terms of how do we look at the future, we want to be able to collect more data from our existing sources and build these databases. One thing that I've been working on is trying to improve the data standardization that's being used in glaucoma research. And we want to democratize access to data sets, ensure trust in data collection. I think now with growth in AI, there's also been concerns about how AI is used, and certainly, unless you've been living under a rock with all the advancements with ChatGPT and use of AI, I think there's a lot of concern about bias and hallucinations, false information. And so this trust aspect, I think, is even more and more important. Of course, as I mentioned, we want to continue to fund new data sets and building a diverse workforce to make sure a diversity of representation is included. I know we're running short on time, but just very briefly to talk about data standardization. The reason this is important is multiple. One is that for clinical interoperability, we need to have better information transfer between our clinical information systems, and this continues to be a challenge. But from a research standpoint, it's also important for data extraction and data sharing. And Anthony and I have been very lucky to be able to work with standards organizations like SNOMED to try to improve the standardization and representation of glaucoma-related data elements. And also we need to have improved data entry to make these data more reliable. I always, I like this figure. It shows kind of this garbage in, garbage out idea that everyone always talks about. You might have lots of data, but it's not that useful if it's all sort of garbage or not well organized. But I do want to just express maybe a more optimistic outlook. I had the pleasure of raising some backyard chickens while we were still in San Diego. Husband thought it was a good idea, even though we had 3 kids during residency, and why not throw some chickens on top of that? But one thing that I did learn from the chickens was that you can have things that are literally garbage, like food scraps and things you would have thrown away, like moldy bread and like produce that's overdue, and they'll turn it into these beautiful, blue eggs and brown eggs. And this idea of how can you take something that is less than ideal and turn it into something better, I think has really motivated a lot of my work in data standards. And even if you have something that's disorganized, messy data, I think that's really our challenge as data scientists. And we need clinicians and researchers to inform that data transformation process and try to make it more usable and better for research and for improving patient care. So with that, thank you very much. I look forward to discussing some of these during the panel.
Garbage in, but pearls out. That's a great concept. And thank you for that wonderful overview. Our next speaker is Anthony Khawaja. He is an associate professor and honorary consultant ophthalmologist, UCL Institute of Ophthalmology in Moorfields Eye Hospital. He's a senior research associate there. Anthony is amazing. He's currently the UK Research and Innovation Futures Leader Fellow and a Lister Institute of Preventative Medicine Fellow. His research began with a Wellcome Trust-funded PhD program at the University of Cambridge, including a Berkeley Fellowship-supported period at Harvard Medical School, and we spent time together when he was with us, and that was a really wonderful time for me. Anthony's research interests concern the genetic environmental causes of glaucoma, and his ultimate aim is to develop prediction models that can enable efficient patient screening of glaucoma and more personalized care of glaucoma patients in the clinic. Recent awards include American Academy of Ophthalmology Senior Achievement and Secretariat Award and a National Health Service Bronze National Clinical Excellence Award. When you see him, these accomplishments are really remarkable. And every time I go on PubMed and put in glaucoma, I see Anthony's name, and I'm always amazed. I'm learning something new every minute. And so thank you for being with us today, and we take it over.
Okay, thanks very much, Lou. That was a really nice introduction. And thanks to the Glaucoma Foundation for inviting me to be here with you at really what is quite a unique meeting. I'm really looking forward to it. So I'm talking about UK Biobank. I think this is well known now. You probably all know the study that started in 2006, a huge prospective study. At that point, there weren't studies this size. 500,000 people recruited across the UK, funded largely by the UK taxpayer and also some of the UK charities. But what's really quite special about UK Biobank is that we have eye measurements in it, and quite a lot of eye measurements. Sometimes eyes are left behind when you're doing a study for general health, and really, we're lucky in the UK. We've got people like Professor Sepeng Kaur, who's well known not just in ophthalmology, but across medicine in general, and he strongly advocated for why eyes need to be part of UK Biobank. So for over 100,000 of the last participants, there were detailed eye measurements, and that this is a sped up version of a video they made to show they could fit in 6 tests in 10 minutes. Because when you're measuring so many people, it's really expensive. And so they proved we could do that, including this, the ocular response analyzer, which I'll come on to. But why do you need such a big study? So when they set out to do this, why? We've got lots of population-based studies. Why do you need one that's got 500,000 people in it? Well, this is one of the reasons anyway. We all know that if you've got a higher systolic blood pressure, you've got a higher chance of having ischemic heart disease in the future. But is that risk the same if you're aged 45 or 85? Maybe blood pressure only matters when you're older. And here, this is it stratified by age group, and you can't really see what's going on there. That's with data from 5,000 people. When you go to 50,000 people, you start to see a pattern there. It seems no matter the age group it's going up, but we're a little less certain with the younger people. Now with 500,000 people, look at that. You can see clearly the effects by age group, and that actually the effect might be stronger in younger people than in older people. And this is what's known as an interaction, a statistical interaction. And to be able to look at these clearly, you need really large sample sizes. And I'll show you later how we've leveraged that to better understand glaucoma. So let's go on to one of those measurements. You all know the ocular response analyzer. It's a non-contact tonometer that, unlike conventional non-contact tonometry, which measures just that inward applanation, keeps pushing the cornea in and measures another applanation on the way out. And it's a linear combination of those two pressures that gives you the corneal compensated intraocular pressure that I and many other people believe to be the best measurement of intraocular pressure that we have, because it reduces corneal artifact. And so through UK Biobank, we now have the biggest study looking at what the determinants of this measurement is. This was striking. I remember when a fellow PhD student of mine presented her work at first, and she showed this, the relationship between IOP and systolic blood pressure. And my first piece of advice to her is, well, can you please put the error bars on those products? She said, no, the error bars are there. Look at the people with the systolic above 190. The data was so precise that the error bars were smaller than the spot for the effect size. I'd never seen this before. And actually, if you look at that trend, the p-value, it's the first time I came across a p-value that was too small for my statistical software to present. It was less than 10 to the power minus 350. So we already knew that blood pressure is higher with systolic blood pressure, but that then gives you real strength to look at other things. The other thing, Sally alluded to this, within one study, you have people of multiple ancestries. And this was interesting. The Goldman correlated intraocular pressure is lower in black people by almost 1 millimeter of mercury. That's a large effect size in epidemiological studies. Yet black people have more glaucoma, don't they? But when you look at the corneal compensated intraocular pressure, the true one, it flips by a huge amount, and they have a considerably higher intraocular pressure. And this just confirms what we know. We know black people have thinner corneas, maybe softer corneas, and that we tend to underestimate the pressure in them. Maybe that leads to late diagnoses, I don't know. The other thing, around this time, me and others questioned, why aren't we finding more genetic associations with intraocular pressure? Surely we know it's genetic from twin studies and family studies and so on. And this was the summary of where we were at really before UK Biobank. There are around 7-8 points in the genetic code, which each contributed to IOP a little bit. And we said, why is this? Surely 35,000, that's a big sample size. Maybe it's because we're measuring IOP in different ways. Maybe it's this corneal artifact, what's going on? So with UK Biobank, suddenly we've got a huge sample size, over 100,000. IOP is measured in exactly the same way and maybe in a better way. And where did we get to? So this was, I certainly don't want to steal Stuart's thunder, but really it was UK Biobank that provided this step change. All of a sudden, there are over 100 points in the genetic code that are influencing intraocular pressure. And the amount of novel biological signal in that is huge, and I think we're still making sense of it. And you can look at pathways when you do that. Two of the most interesting ones for me were developmental processes coming out so strongly. So the way I interpret this is actually what happens to your intraocular pressure as an older adult is predestined in your genetic code and in the microanatomy. So some of us are born with a microaqueous outflow system that's built to last 150 years and they won't get glaucoma. Others are built to last maybe 50 years and it starts to decompensate. But the clues are there already at the time of birth. And this was a really huge one for me. The number one pathway, biological pathway for IOP in adults was for lymphangiogenesis, and it points to Schlemm's canal and collector channels. And that really challenged the dogma that POAG is a disease of trabecular meshwork. And this opens all sorts of other ideas, which Stuart may well go into. One of the jaw-dropping things was when we sent this data to Lou and others in neighborhood to say, well, these variants that are associated with intraocular pressure, are they relevant for glaucoma overall? So this completely independent data set. And this graph came back to us. I mean, you never get this in science. This was almost a linear relationship. Basically, anything that genetically puts up your IOP by a little bit, puts up your risk of glaucoma by a little bit. If it puts up your IOP by a lot, it puts up your risk of glaucoma a lot. Essentially a very similar thing. Now, I think everyone here knows how important IOP is, but this certainly cements it in terms of the genetics. The other question is can we, by just using those genetic variants, then predict who's going to have glaucoma in neighborhood? So can we make a formula out of those genetic variants and see who's going to get glaucoma? Now, the area under the curve for high tension glaucoma was 76%. Now remember, these are genetic markers that you can measure at somebody's birth. You've got no measurements of the patient as an adult, and yet that level of accuracy. And that's the sort of level where it starts to have clinical utility. Even for normal tension glaucoma, it was 71%, again confirming what we already knew, that IOP is really important in normal tension glaucoma. And why was this exciting? I think we all struggle in the UK and in the US. Population screening isn't recommended, despite glaucoma being irreversible, asymptomatic in the early stages. We can't screen the populations because our tests aren't good enough. And that's because even if you apply a good screening test to a population with a relatively low prevalence of undetected glaucoma, it doesn't perform well. Nearly 9 out of 10 people you'd be sending to the hospital won't actually have the disease. And we imagine this future, which is coming, where all people interacting with healthcare services are genotyped, you can target that screening test to just an enriched subset with a much higher prevalence of glaucoma. Now, nearly half the people you're sending to the hospital will have the disease, and that might be cost effective. And I think that will be the first way we'll see changes. And just to say that, the UK Biobank really helped with this, because we've seen now it's a lot about sample size, and we're about to do another bigger study bringing together all of the IOP data available globally, and we're expecting to double our discovery. But it was the UK Biobank that first brought in this step change. One of the other tests was macular OCT. I remember at the beginning, all the glaucoma doctors were a bit disappointed we didn't do the optic disc. And at that point, it wasn't so clear how robust the inner retinal layers would be, or even if we could robustly segment them to learn about glaucoma-related processes. But Over time, that did become possible. And we have some of the largest studies describing how the inner retina varies across the population, across ethnicities, across different groups with others, according to systemic parameters. So when a PhD student I was working with came up with these Manhattan plots for the genetic determinants of these two layers, I was, wow, we're going to learn so much more about glaucoma. But unfortunately, actually, a lot of the genetic determinants of inner retinal anatomy don't seem to be related to glaucoma. We did find some interesting things that I think are going to be important confounders and will help us better understand who has glaucoma or not. And one of these things is the localized effect by genotype. So this was the top variant that affects inner retinal thickness. And you can see across genotype, the change in thickness it's universal across the whole macula. But these were two loci that we know about, because we know there are very rare mutations in these genes that can cause foveal hyperplasia, in Mendelian foveal hyperplasia, and quite profound vision loss. But these are common variants in these genes that many of us in this room may have one or two of, and they have their effects predominantly at the fovea. And these variants are also associated with visual acuity. So it turns out foveal hyperplasia is not just an extreme phenotype, it's something that we vary across in this room even. Right, something that I think's probably of particular importance to the Glaucoma Foundation and to its members are modifiable risk factors for glaucoma. So many of our patients ask us, okay, other than these drops or this surgery you want to do, what can I do in my life that will help? Also importantly, if we are imagining that future where we're doing genetic testing and we're going to identify people at high risk of the disease before they have it, we need to empower them with the behaviors to reduce that risk. So that was the motivation for putting together the modifiable risk factors for glaucoma collaboration, including Lou and Jay He and many others, because you need lots of different expertise to come together to analyze this data. We started off with something that we all love, and that's caffeine. In UK Biobank, the broadest question on it was just how many cups of tea or coffee do you drink a day, and then what type do you drink? If you're interested what the UK habits are, blue is coffee, but orange is tea. So it confirms what you already knew. UK is a tea drinking nation. But amazingly, nearly 1 in 5 UK Biobank participants drink 6 or more cups of tea a day, which I thought was quite striking. Lou and my other American collaborators thought this was gross, but when the UK participants were asked, what type of coffee do you normally drink, over half said instant. But this was in 2006 to 2010. I think things might have changed since then. But actually, look, we don't get necessarily most of our caffeine from tea or coffee. And in the US, it mostly comes from soft drinks. And it's not just drinks either. So together with our nutritionist experts, we took data from the 24-hour recall data, which was a questionnaire which was administered by email, and we took 19 questions on food and drinks containing caffeine to calculate one number essentially for people's caffeine intake. So, was caffeine associated with eye pressure? The answer is, very little, if anything, slightly lower eye pressure in people who consume more caffeine. What about with the risk of glaucoma? Pretty much no association. But what we need to take into account is someone's genetic predisposition to glaucoma. I'd argue now, in the same way as you'd never compare two groups and their risk for glaucoma if you don't adjust for age, because age is such an important risk factor. If you don't take into account people's genetic predisposition to glaucoma, you can't see the wood for the trees. So, coming back to this, that's why you need that large sample size. So how does the association between caffeine and eye pressure and glaucoma vary by the genetic predisposition to glaucoma? And you can see it here, the 4 lines are the increasing genetic predisposition to glaucoma. And it's only those who are most genetically predisposed does a higher usual caffeine consumption associate with a higher eye pressure. That's a gene-environment interaction. It's significant. Those who are in this field know it's not that often you get a significant interaction. Similar with the prevalence of glaucoma. Only those in the highest genetic risk, in purple there, does the prevalence of glaucoma shoot up with the highest level of caffeine intake, a highly significant gene-environment interaction. So we wouldn't have seen this if we didn't have a big enough sample size and we couldn't stratify by genetic risk. What's our hypothesis here? Caffeine's an adenosine receptor antagonist. There are these receptors on the ciliary body. We believe that caffeine may increase your aqueous outflow. Now, if genetically speaking, you've got an aqueous outflow that's going to last you 150 years, that's fine. Produce more aqueous. If you don't, then your pressure will go up when you produce more aqueous and increase your risk of glaucoma. The next thing we were most interested in was alcohol. A PhD student in my group looked at this. Actually here, you didn't need to take into account genetic predisposition. You could see higher levels of alcohol intake being associated with higher eye pressure, higher prevalence of glaucoma, and thinner inner retinas. And even at the levels which are within the drinking guideline limits in the US and in the UK. But again, if you looked at the genetics, so those 5 groups are quintiles of increasing genetic risk. And you can see if you're at the highest genetic risk, there's a really quite a steep slope. Actually, if you're in the lowest 20% of genetic risk, you can drink as much alcohol as you want, it seems, and you might not get higher pressure. Right, if I didn't have to submit my slides in time, I could have swapped this for a photo of Manhattan. So of particular relevance, this is something else you can do in UK Biobank, look at local geophysical factors based on where a participant lives. And so we've shown here that people that live in areas with higher levels of small particulate matter pollution have a higher prevalence of glaucoma, not much difference in IOP, and a substantially thinner ganglion cell in a plexiform layer, maybe suggesting on a larger scale that pollution is a potentially modifiable factor on a population level. I saw, there are various things that we're interested in epidemiologically, like sex hormones. I saw lipids wasn't on the program this time, so I wanted to bring it up because UK Biobank's helped us delve more into this subject because there's a bit of a smoking gun here. And this was interesting. This is just the standard blood level of total cholesterol, HDL and LDL cholesterol. And in 2 separate cohort studies here, there's this really quite consistent association with a higher intraocular pressure. Now, what's really weird here, normally, when you look at HDL and LDL, they have opposing associations. So, for example, with heart cardiovascular disease, higher LDL is associated with a higher risk of cardiovascular disease, but higher HDL with a lower risk. These are going in the same direction, suggesting there's something about lipids, lipid metabolism that is important in IOP, but it's a different pathway to that mediates cardiovascular risk. And further work here led by Lou and Oana Zeleznik, looking at metabolite data in multiple cohorts, including UK Biobank, confirming this strong signal, something's going on with lipids. And it wouldn't surprise me if in 20 years' time we had some kind of new therapy that targeted lipids. It's clearly, there's something there for IOP. You can look at so many things when you have such a big study and cleverly run questionnaires. One example is sleep apnea, where there seems to be an observational association that's consistent. If there's sleep apnea, a higher chance of glaucoma. But actually, when you do a Mendelian randomization study, which is pretty well powered actually, they're not finding an association, suggesting that might all be confounding. But sleep's quite complex. I quite like this paper, which did a sort of components analysis to work out patterns of sleep. So you can have a healthy sleep pattern, and if you tend to snore or feel sleepy during the day, or if you get insomnia or short or long sleep duration, then you're at a higher chance of glaucoma. And luckily for me, I'm a late chronotype. There doesn't seem to be any altered risk. Some new things coming up in UK Biobank. So I think this is the best ophthalmic electronic medical record there is. We don't have it at Moorfield, sadly, but a lot of the rest of the UK has. It collects really structured data in exactly the same way everywhere. It's not like EPIC, where everyone's collecting it in different ways. It's in exactly the same way. It interacts with the visual field, so you get all of the longitudinal visual field measurements. It's got mandatory fields that force people to put the data in. And it's that Medisoft data that produced this great graph from David Crabb's group. Each dot's a patient, and how they're moving is how the visual field's worsening over time in UK glaucoma clinics. And also this data, this is the average response to SLT in the UK, a nice initial drop and then slowly waning over time. But, you know, our patients aren't averages, they're individuals. And here you can see the real spectrum in response. Now, just imagine matching up that visual field progression data, this response to treatment data, with all the genetic data and other biomarker data there is in UK Biobank. Well, that's happening. This was exciting when we first realized this. Those are all of the UK Biobank centers ordered by the number of self-reported glaucomas, and those are the places where the local major eye unit is using Medisoft. And so this has been approved by UK Biobank, and it's underway, and hopefully by the end of the year we will have this linked data, and we're estimating for 15,000 glaucoma patients. The other thing, we're doing more imaging now, and it's the world's largest longitudinal imaging, and we got OCT in there, and thanks to the Chan Zuckerberg initiative, who have given us a lot of money to do that. This time it will include the optic disc as well as the macula, and I really pushed for this. We're getting autorefraction as well, because you really can't understand some of the numbers if you don't take into account the size of the eye. So I want to thank, you know, particularly Pencor and Paul Foster for having the vision to make this happen. The whole consortium, the UK Biobank Eye and Vision Consortium, been very collaborative, and there are many international collaborators too. The UK Biobank model of open access, I think, is still unique. I would argue all of us isn't. I think it's all of the United States, because I think if you're not in the United States, you can't access that data. But that has meant that there's been such tremendous knowledge generated. Thank you all for your attention.
Thank you, Anthony. That was a fantastic talk, and I am in awe. I've learned something, and I'm familiar with the UK Biobank. But let's move on to the next talk, which will be by Professor Stuart MacGregor. He's the head of the QI-MR Statistical Genetics Group based in Brisbane, Australia. You know, Stuart's work is disruptive. Over the past 20 years, he's made seminal contributions to our understanding of complex trait genetics for a wide range of diseases. He's got 275 publications, 25% are in glaucoma, and we're really fortunate that it's high, but we'd love to see it higher, because the stuff he does is amazing. He plays a leading role in consortium science, and that's going to be a theme here, as you could hear, is like collaboration, international collaboration. That's what's going to help us in glaucoma, particularly in the area of genome-wide association study. His work developing and applying statistic genetic methods has led to publications in top journals such as Nature and Nature Genetics, where he has 26 publications. Stuart's received many awards, including the Australian Academy of Science Human Genetics Medal and the QI-MR Berghofer Breakthrough Award for his work on glaucoma genetics. In addition to his academic work, he's a co-founder of Cenex Bio, a startup that seeks to improve the treatment and prevention of blinding eye disease through the development of advanced risk prediction tools. Stuart, thank you for coming all the way from Australia, and we're very excited to hear about your work.
Great, thank you. Thank you very much, Lou, for the kind introduction, and thank you very much to the Foundation for the opportunity to share our results. It's terrific to be here. All right, so as Lou mentioned, just a couple of disclosures. I do some commercial work. The work I'm presenting today is purely on the academic side, focusing on our collaborative work, and I'll get to that in a moment. Much of what I'm going to present today is subject to a paper you'll be able to read should be next month. It will come out in Nature Genetics. That's the cover image we submitted to the journal to hopefully get some additional publicity for the study. But we'll see. We haven't got confirmation yet about whether they selected that image or not. But combining the eye and genetics. All right. So what I'm going to talk mainly about open-angle glaucoma. I'm going to focus particularly on the disease itself, but also on intraocular pressure and vertical cup to disc ratio. So, and I'll show you in a moment about why those together are more than get you further in terms of things like drug discovery or prediction than just looking at glaucoma alone. And one of the ways which we would potentially move forward by leveraging those correlations is by getting some insights which are beyond pressure lowering, so going beyond the extent of current treatments, which only focus on lowering pressure. So glaucoma, from my point of view, I spent more and more time, particularly over the last 5 years, looking at glaucoma genetics, and it's quite easy to motivate that because glaucoma is one of the most heritable of all human complex diseases, and so what we've done, particularly in recent years, so I mean, my work began with some of the first Genome Association studies about 12 or 13 years ago, but really discovery has ramped up, in particular since UK Biobank and some other data sets brought very large scale sample sizes, but all of those are under the paradigm of what are called genome-wide association studies. So in the simplest case, it's looking at difference in allele frequency between cases and controls at markers all the way across the genome. It can also be done for quantitative traits by looking about whether having a particular allele increases your intraocular pressure or your BCDR or other quantitative parameters. So that's going to be important for three reasons. I'm going to mainly talk about the first one, so that's about new biology, about finding new drug targets. I'll mention briefly causal inference. Anthony also covered a bit of that in his talk about how we might find links between modifiable risk factors and disease. And then at the end of the talk, I'll talk about predicting disease outcomes, which I think is very exciting in the context of glaucoma. All right, so in terms of drug discovery, so one of the reasons for the excitement and the reason for trying to uncover the genetics of diseases such as glaucoma is to do with drug development. And so this is a paper from a few years ago now, and then a follow-up study looking about how we might use genetic data to improve drug discovery. So actually, take that one off. Across a range of different gene mapping studies, it's become clear that if you have a target which is supported by genetic evidence, then the risk of that compound making it to clinical use is about double, which in the context of saving money in the drug development pipeline is enormous. One thing I'd make clear, it's a common misconception, I guess, is that the effect sizes from the studies which I'm going to show you are very small effect sizes. So you might get a particular allele which increases your risk of glaucoma by 5%, 10%. Just because the natural effect sizes occurring in the general population are relatively small does not mean that particular target cannot be modulated to a clinically effective degree by pharmaceuticals. And there are many examples where the naturally occurring effect size in humans is quite small, but you can apply a drug to modulate that particular pathway to actually get a clinical impact. All right, so in terms of how we can maximize our power, how we can find new genome-associated associations. So the starting point I'm going to take is a large study from the International Glaucoma Genetics Consortium, which includes Lou, Anthony, and many other people from around the world. It's been an amazing collaboration. We still talk every month on a telecon. We've done it for many years. It's been a fabulous collaboration. Basically, it stems from the fact that we're realizing that when we want to understand genetics, we need very large sample sizes. We must collaborate, and so it's been a great model. The study we published a couple of years ago found 127 risk loci for glaucoma, but really to go beyond that, we have to use smarter approaches. So both the largest possible sample sizes, but also the smartest ways of using different traits. So I mentioned intraocular pressure and BCDR. So those are highly genetically correlated with glaucoma. And the exciting thing from the point of view of getting big sample size so we can get a lot of genetic discovery is the fact that these can be measured in the general population. Anthony mentioned there's over 100,000 people with intraocular pressure measurements. There's a large number of people with BCDR measurements. So you can actually use people in the general population to actually map. You can probably map more genes in the general population for glaucoma than you can by looking at glaucoma cases and controls. So there are ways of combining those. I won't go into the details here, but you can do a multi-trait approach, which basically combines information across correlated traits. It works amazingly well for when you have conditions like IOP and VCDR, which are strongly genetically correlated to the target disease of glaucoma. And on the right-hand side here, I'm showing you that basically the star is where we were at a couple of years ago in terms of genetic discovery, and these are just modeling extrapolations for how much. How many more loci and how much of the disease we would explain if we had bigger sample sizes. And so I'll show you as we go through the talk, we can essentially do better. We can get from 100. So this is the prediction we published a couple of years ago about where we would get, and I'll show you where we move up that as we increase the effective sample size. So in addition to increasing just pure sample size, we also looked at different ways of getting smarter phenotypes. So we looked both in UK Biobank and in a large Canadian cohort, which has a lot of retinal imaging data, and we looked to see whether you could use, rather than using, so starting in UK Biobank, we painstakingly characterized about 65,000 images by manually. To basically grade their VCDR and then use that to train our artificial intelligence model, which gets you more accurate measures of VCDR, which gets you a lot more genetic discovery because the phenotype is much cleaner, and so you get some insights into VCDR, and I'll show you in a moment how we leverage that to find more genes for glaucoma. You also get some really interesting insights, and in the interest of time, I won't spend too much on this, but essentially we can look and you can see when you have this. When you have this AI-derived BCR phenotype, you can see really subtle but important differences between different human populations. And this work was published actually in a kind of interesting, competitive, but exciting approach. I guess we were competing with Anthony and the Google group, and in the end we published these studies back to back in it. So it's I guess some of these competitive approaches which are driving our work forward quickly. So to leverage these large sample sizes, we took data from different major human populations within the International Glaucoma Genetics Consortium, and we took data first of all across the top for Europeans. We took our glaucoma case control studies. We added in data from VCDR and intraocular pressures, so the sample sizes are quite large for those, so you get a lot of power there. So essentially, you get an output results for Europeans. Do the same thing in the other major populations, combine all of those together, and we get a cross-ancestry result, which basically gives us more power to identify new loci for glaucoma. And so we get an overall cross-ancestry result. We starting in Europeans, which for various historical reasons were the largest sample sizes. We found many loci, and we found that we got fairly good concordance across different ancestry groups. So we got correlation of about 0.75 between the European effect sizes and the Asian effect sizes, and a smaller correlation of about 0.5 with the African effect sizes. So there's not the genes in glaucoma are not exactly the same across different ancestries, but there's a lot of overlap, and I guess this is reassuring in terms of making sure that when we make discoveries in one population, they might be useful for other ones. I think there will be some unique ones, and there's a few publications suggesting that, but I think overall there's a pretty clear correlation across different groups. And so then this is our headline findings. There's so many loci here, you're not going to be able to read the details, but we found basically by combining this artificial intelligence-derived VCDR and very large sample sizes, that essentially we've increased the number of loci 2 years ago from 127 up to 312. And so essentially we're finding many novel loci, and I'll talk you through some of those in the coming slides. So that was the work from our consortium and leveraging correlated traits. We also sought to get independent replication to be sure that we're not finding artifacts as a result of this model, which is combining glaucoma and BCDR and IOP. And so we're able to get excellent replication from the personal genomics company 23andMe. So essentially all of the loci replicate. So these are all very high confidence loci. In terms of genetic architecture or genomic architecture, so you can kind of see the cyan dots are the new ones that we're adding in. You can see the curve there. That's essentially the power. So it's essentially we're coming up against the edge of power to find new things. But it's pretty clear that we're finding across a range of different allele frequencies on the x-axis, we're getting effect sizes which are explaining the variation that's there. So we're getting a lot of findings. There's more scope to find things. In the interest of time, I won't show you the graph, but essentially this number of novel loci is exactly what we predicted we would find before. And I think with bigger sample sizes, including some of the studies that Anthony mentioned, I think we will find more loci, we'll get more insight. In terms of our design here was a study mainly looking at common variants. So that's why there's not too many on the far side where you're looking at rare variants. But what we did look at was just looking at some of the established loci from family studies. We do see the expected stop codon and mycilin. We saw a common variant in optoneurin, which is completely unrelated to the rare variant found in family studies. Although in general, so there's some concordance there. Although in general, the findings from sequencing studies, so exome sequencing and whole genome sequencing, have been relatively disappointing. In the UK Biobank exome sequencing study, you get a significant locus with sequencing, which you can also find by GWAS. And we found a couple of loci which are not actually don't even reach significance in exome sequencing of 500,000 people in UK Biobank. In those particular genes, we actually found some common variants as well. And so we're getting some examples of where the same gene can be perturbed by both rare variants and common variants. But in general, I think most of the future discovery will be from large scale studies looking at common variants rather than by sequencing studies, because sequencing studies are essentially the biological reality is the effect sizes are pretty small. And so you would probably need to find many loci from sequencing. You probably need sample sizes in the tens of millions before you find too much. So I think a lot of the utility in coming years will be from the common variants. And those results are from the AstraZeneca exome sequencing results platform. So just to unpack what some of those novel genetic discoveries are doing, we're looking at a range of different methods. We're looking at classifying them in terms of their effect on IOP or VCDR. We looked at gene-based tests. We looked at expression or splicing QTL studies. So that's ways of just looking about what does a particular variant change expression in relevant tissue types. We looked at transcriptome-wide association studies, looking at plasma proteomics studies, as well as cross-strait studies. So I'm going to go through some of these in the interest of time. I'm not going to have time to go through all of these, but there's different ways you can try and interrogate what's there. All right, so as a big picture overview, I'll go through some specific ones in a moment. About 2/3 of the loci we're finding are loci which are driven by intraocular pressure. About a third are BCDR loci. We're not really finding many loci which don't go through one of those pathways, which is partly because of the design. But even when we look at studies looking at just glaucoma, there isn't really much else there in terms of genetic mechanisms. We find a large number of genes when we do gene-based results. We won't talk too much about pathway analysis, but obviously some of the interesting things that have come out have been things like the angiogenesis pathway that Anthony mentioned. We found TWAS studies, PWAS hits, which are ones to do with proteomics levels. And in terms of drug prioritization, we've got 69 potential targets, 17 of which are high confidence because we've got multiple levels of genetic evidence. And I'm happy to discuss this in the discussion, but I think one thing is clear is that the novel targets that would be expected to benefit most patients, they're not going to be specific to people who carry a particular mutation, but happy to chat about that afterwards. All right, so in the interest of time, I'm just going to look at a small number of the novel associations. These are two of the novel ones, is TCF7, TCF2. So these are on different chromosomes. So they're in obviously the related genes. But what's fascinating, I think, here is we're getting evidence linking the particular mutations through expression QTL, and those in this particular case, they actually act through different mechanisms. One of them seems to affect BCDR, and one of them affects intraocular pressure, and they're also associated with other glaucoma phenotypes. And so it's when we get in the level of understanding individual loci, the mechanisms are relatively complex. In terms of drug targets, this is just a summary of some of the ones which have come up in terms of ones which are driven by intraocular pressure. So we're seeing some interesting links, which I think will relate to some things later in the program in terms of looking at. These are particular genes where there are existing drugs acting on diabetes or other pathways, and so these are novel findings from the GWAS hits that we have. They're supported by multiple links from the genetic code to the to particular gene expression or proteomics implications, and so we're getting many genes implicating these drugs, I think, which will be very interesting for future work. And that's the ones for intraocular pressure. I guess what's exciting is that this approach found many genes for BCDR. So these are obviously extremely interesting neuroprotection targets. So again, where possible, we map through multiple different criteria. We're getting co-localization with the same variant effects, both expression and the trait. And we've got a range of different drugs which we think are excellent and exciting candidates in terms of repurposing those for use in glaucoma. All right. We'd also looked at cross-trait relationships. So, for example, we're getting links between education and blood pressure, which because of the large sample sizes, we're getting a much clearer picture there than in previous studies. We're getting some links through using causal inference to link between, for example, autoimmune disease and glaucoma for the first time because the sample sizes are very large, and we're getting some co-localization, which I'll cover in, which I can discuss further at the end. So for the last part of the talk, I'm just going to mention briefly about risk prediction. So this is something which is enabled by the large sample size I've got here, and I think it's something that's very exciting in terms of translation. So because glaucoma is so difficult to diagnose, because there are essentially no environmental risks which have a large impact, then a genetics-based approach has excellent potential in terms of predicting who would benefit from enhanced screening, from earlier treatment. And so Anthony mentioned polygenic risk score. The basic idea here is just basically combine effect over many loci, and so that top snip there is one in TMCO1 gene. If you have for every extra copy of the TLL, your risk is reduced by about 30%. So essentially, for each person in your study that you want to get prediction of that person's individualized genetic risk, you can sum up the effect over all the genes that we know about. In this case, it's going to be thousands of markers which have at least some evidence. And so essentially you get a risk stratifying score. So this is like this is not a diagnostic test. This is not say that your person will or will not get glaucoma. It's a risk stratifying score. Perhaps you might think about it like a cholesterol test. Well, basically a person who has a much higher risk, so it might be smart to make some decisions based on that rather than claim that this is a diagnostic test. So it's a common misconception with some of these studies. So it's a risk stratifying score. So we published previously on this, and you can predict risk well, you can predict age of onset well, and you can get some associations with clinical outcomes. So I'm going to show you some improvements over that study from 3 years ago. And one of the innovations that we added was with the large sample size, because there's differences in prevalence by ancestry. We wanted to look and try and get predictions which would be effective in as many human populations as possible, particularly recognizing some of the populations at high risk, like African ancestry populations. And so when we're looking to build prediction models, because historically many genetic studies have been based on Europeans, when you try and build prediction models and apply them to other ancestries, the further away they are genetically from Europeans, the more difficult the prediction is going to be. And so the most difficult predictions are going to be for Africans, and Asians are expected to be about halfway in between. So it's going to be difficult to get predictions that work in all populations. But essentially, what the model I showed you before was doing is basically if we combine data across different populations. I won't go into the mechanisms about how we construct the PRS, but essentially there are ways of leveraging the power from the biggest studies in Europeans and the more specific results in Africans, for example, to improve predictive accuracy. And I'll just show you a small number of results. So essentially, this is using our model built and fine-tuned to be effective in prediction in Africans. A lot of the power comes from a study in Europeans. So for example, if you train the model just using African genetic studies, they don't do so well. But if you use a combination of European and African, you can get better predictions. And so for example, this is an application to the Adagi study from Bob Birmingham's group. And so we can get good prediction of risk in that population where it's been historically difficult to predict risk in that group. We get better risk stratification than we got previously. This is an example in South Asians from UK Biobank. So you get about an 18-year difference between the bottom 20% and top 20%. So you can get a good stratification of who will be at highest risk. And just the last thing I'll mention in my talk is looking at lifetime risk. So this is something which is a problem. Anthony mentioned it briefly in his talk. If you get a top score for a disease like Alzheimer's disease, if you get a top 10% score for your genetic risk for Alzheimer's, your absolute risk is pretty high because it's a relatively common disease. But in glaucoma, because it's relatively rare, even if you have a high score, this is based on the PRS that we published a few years ago in 2020, your lifetime risk is still not high. So it's not high enough really to really have a large impact. But one thing which I think is really interesting in terms of actual translation of these scores is looking at people who have family history. So this study from the FinGen study, which was published last year, they look at whether family history and whether a polygenic risk score, what sort of information you get from those sources. So a person's self-report family history or family history from medical records in the case of the FinGen study. And they actually found interestingly that there's not much overlap between family history predictions and polygenic risk score predictions. I think in the future, when we develop more accurate predictions, there will be more of an overlap. But for now, they're relatively independent. If you have a model and you fit polygenic risk score first and then family history, the family history adds, and if you do the reverse, it also adds. So for a wide range of different diseases, including glaucoma, that's true. So in terms of practically getting predictions for who is going to be highest risk now, we want to be ideally recording family history as well as using a simple saliva test to calculate a polygenic risk score. I show you some of the results just from our very recent studies. So this is unpublished work, but essentially the documented risk prediction is high for family history. We looked in two studies. We looked in a Canadian cohort study, Cartagene. We asked a question about if they have an affected sibling. And if you have an affected sibling, your risk of glaucoma is 6-fold higher. We did the same thing in Q-Skin, which is a cohort study based in Queensland, Australia, in the institute where I'm based. So skin cancer focused study, but we added questions in about people's parents and siblings having glaucoma, and so having a first degree relative with glaucoma increases your risk about 3-fold, and if you have a sibling, it's about 5-fold. So you're getting so having family history is an important predictor of a person's risk. And excitingly, if you combine these things together, so the polygenic risk score and the family history, we get an excellent degree of risk stratification. So the most exciting finding here is basically on the right-hand side of the graph, about a third of the sample, if they have family history and they have a top 20% PRS, have glaucoma in this Canadian cohort study. So you're getting their absolute risk is really high for these people, and so that's something that can be directly used, both in terms of prediction, but also in terms of ensuring things like eye drop adherence, which is very difficult. So informing these people that their risk is ultra high as a result of their combination of their family history and their PRS, I think it's important. We also looked at that in the Q-Skin study. So this is our Australian study, and we saw a similar result. Happy to discuss it more at the end, but we also looked at not only if you have one first degree relative, but if you have 2 first degree relatives. This is not that many people. It's about 1 in 200 of our cohort. But in those people, remarkably, this is only on 10 people in that top group. But in this group of 10 people who have a family history and have a top 20% score, then 90% of these people have glaucoma, which is remarkable. And in the people in the lowest group, it's only 1 out of 10. So we're getting an amazing degree of risk stratification, which I think has big consequences in terms of how we might roll out these scores and actually use them in predicting absolute risk. So what we're doing now is we're gearing up to feedback these results in our large Australian cohort, as well as in other contexts, including information on family history, as well as simple PRS scores. So in conclusion, our study using a multi-rate approach finds over 300 loci for glaucoma. We're using that to find exciting new drug targets, including ones for neuroprotection. The consequences of these large sample sizes are that we're getting excellent risk prediction. There's still more work to do to ensure that prediction is effective in all human populations, but we're definitely getting there. And combining PRS with family history, I think, is a very exciting approach in terms of actually getting useful predictions. So I'll finish by acknowledging there's many people involved in this work. In particular, there's people on the slide from the International Glaucoma Genetics Consortium, many of my local Australian collaborators and funders, as well as, of course, the studies like UK Biobank, a couple of Canadian biobank studies who've been very forward-thinking in their approach to data sharing, and it's been something that's really driving the approach we've been doing. So just like to say thank you. Thanks again for the invitation. It's been great. Thank you.
Thank you. That was fantastic. So our last speaker, unfortunately, has canceled. And the goal of his talk was to use cardiovascular disease as a model and to integrate all of this stuff, the genetics, the imaging, the electronic medical record using AI. I couldn't possibly reproduce his talk. And I think it works out for us because it's 9:12. And I think there's pent up energy in the room. And I think this is the time to begin the discussion. And so we had a replacement talk, but we'll pass on that. And I think we'll open the floor for discussions of just an amazing group of talks that you just heard. I mean, really, when you think about it, we've come so far. Remember, I showed that slide of exponential growth in glaucoma knowledge, and I think that you've heard some granular information that speaks to that. And so we don't have mics in around, but oh, great, we do have a mic. So if people want to
raise your hand and I'll come to you.
Great. So while people are thinking, I'll ask a question of Sally. Sally, so you talked about data standardization and use of real world data to help us learn more things about glaucoma. So we're contributing to Anthony's study where he's trying to increase the number of IOP genetic biomarkers, because clearly that's very important. But when we go look through our electronic medical record, we find IOP measured with eye care, Goldman. We don't know how accurate those numbers are. Sometimes they're done by technicians, sometimes they're done by doctors. There are multiple measurements on any one given day. How can you help us with data standardization to address that problem?
Yeah, it's interesting that you bring up IOP because that was one of the areas where we did find some gaps in the current standard terminology representation. So for example, what we did was sort of a systematic analysis through EHR data elements to see how glaucoma-related data elements were represented in various EHR systems and whether they had representation in standardized terminologies like LOINC and SNOMED and so forth. And one of the areas was for IOP. And so there was a codes for just intraocular pressure, right eye, left eye, but there was no way to indicate the method of measurement, like eye care or using a tonopen or Goldman tonometry or applanation. And so we actually, our group recently met with SNOMED to go over how to codify that and then be able to represent the method of measurement. And another gap that we found was there was no standardization or even a code to represent target IOP as well as maximum IOP. And these were things that were felt to be important to be able to represent separately. And so I think, you know, having a way to represent those different methods of measurement, for example, would make it possible that if you were to do secondary research of that data and say, I only want to look at, you know, the ocular response analyzer, corneal compensated IOP, you could then query for those specifically and be able to look at that. Or if you say, I only want Goldman IOPs, that would make that possible. So that's a one example of why the standards are important. And if you don't even have sort of the codes to be able to represent that data, then it would be impossible to disentangle the different IOP values.
I'm sure, Anthony, you're interested in that.
Yeah. Is it, how do
No,
I-
you're
It's
on.
on.
And then there's a question. Dr. Weinrab has a question after Anthony responds.
I think it's just to share with this group what we're doing. So we've set up now an eye care clinical reference group for SNOMED International to do this fairly unglamorous work of trying to sort out the codes. There were lots of missing codes. There was no primary angle closure suspect or whatever there is now. And there's, the shortfalls in IOP, and there is, but we then need to get international sign-off for that. And so we're working with the AGS, the EGS, maybe the WGA to then get sign-off for it. And the out of that will come a short list or a preferred list of codes, which we would then hope would be adopted widely, so that no matter which system you use, you derive fields which fit in with these codes, and hopefully that will make the research easier in the future.
Dr. Weinrab?
Well, first of all, those were amazing lectures, and I'm just blown away by all the lectures, and thank you. I have 3 questions, and they're simple questions, and perhaps they're simple answers too. The first one I'd like to perhaps address to Anthony. Great information. Congratulations on all the amazing work that you're doing. You talked about all the efforts that you did manually to calculate disc area, but yet all the data you presented was using the vertical cup disc ratio. And I'm wondering if you can just comment, if instead of using vertical cup disc ratio, you use disc area, would the results be any different? And just to bring everybody onto the same playing field here, small discs, those discs with small areas, often can have small cups, but yet be glaucomatous. And clinicians in the room know that large discs can have very large cup disc ratios, vertical cup disc ratios, but be completely healthy. So I'm just wondering, should we be considering disc area, or do we do as you did in all your data that you presented, be looking at vertical cup disc ratio?
So no, we have to look at disc area. So one of the strongest hits you get for vertical cup disc ratio is in ATOH7, an important developmental gene. And that's by far the strongest disc area hit. But when you adjust vertical cup disc ratio for disc area, that almost goes away, suggesting that that's more to do with the size of your nerve rather than any tendency towards glaucomatous optic neuropathy. And so we have collectively published GWAS for vertical cup disc ratio adjusted for vertical disc diameter or disc size. And I agree with you, it's really important. And I think any algorithm moving forward, even, for example, looking at AI algorithms that are looking to diagnose glaucoma. For example, some of the work I did with Google, they've got a great algorithm, probably the best one around, at looking at whether somebody should be referred for glaucoma assessment from a fundus photo. But we looked at that on some Moorfields data, and we saw some of the false positives. A lot of those were just large discs. So I think our AI algorithms and our genetic prediction algorithms absolutely need to take into account disc size, and they do. And we've been doing
moving
that.
forward, it'd be very interesting to see some of your data using disc area rather than just vertical disc.
Yeah.
Vertical cup disc ratio.
Essentially, disc area, if you made a polygenic risk score from it, it's not very predictive of glaucoma at all. And so that confirms what I think many of us have thought, that even though a larger disc may have a larger cup disc ratio, a larger disc on its own doesn't necessarily lead to susceptibility to glaucoma.
Great.
I just add one other brief thing on that. So I apologize. In the interest of time, I didn't really spell out in my talk. But when I was saying BCDR and I was using that in the multi-straight model, that's BCDR corrected for disc area, because we found the correlation with glaucoma was higher when you corrected for disc area in the model. So it's a great point. Thank you.
That's what I was looking for. Thank you. The next question, perhaps Anthony and Stuart, you can both comment. Again, very simple question. Current glaucoma management has three essential components. We stage the disease. Is it early? Is it moderate? Is it severe? We look at the risk of progressing, so we do risk stratification. And then we also like to look at the rate of progression. And that helps us decide, how we allocate limited healthcare resources. And I'm just wondering, most of the talks you gave were focused on the risk of glaucoma. And I'm wondering, maybe start with you, Stuart. Can you comment on what information do we have on using these data for looking at the rate of progression? Can we use genetic data to look at how fast somebody is progressing rather than just doing a cross-sectional analysis and looking at those patients with bad disease, early disease, and assuming that the ones with early disease may be progressed faster, because that might not always be the case, because it might not always be linear.
Oh, great. Yeah, thanks for the opportunity to clarify that. So it's something we've thought about a lot. It's I guess in an ideal world, in terms of genetic prediction, we would build a very large data set of people with progression data, linked genetics there. It's just practically speaking, that's very hard to do. And so then that's why we've been focusing so much on risk. But what's exciting is that actually the same genes which predict risk in the general population tend to do pretty well in terms of predicting progression, at least in part because you're talking about an age-related condition. And so genes for risk are also tied up with genes for age of onset and tied up with genes for progression. And so our previous PRS from 2020 did show that there was a good correlation between the PRS and retinal thinning, even measures like need for surgery you could predict from the PRS. Obviously, the new PRS we have now is better than the one we had then, and so it's an area we're looking at right now. I didn't cover it in the talk. That's something we're actively working on about. So it does look like the predictions for risk do a good job. Yeah, for sure. If we had big data sets to train the model for progression genetics, then yeah, that would be better.
So have you looked at any serial data sets to look at over time to validate what you just said? Where actually you have rates of progression.
Yeah, so the 2020 PRS we validated in the Australian Progressor study, which is a longitudinal study of glaucoma progression starting in suspects. And so that PRS built in the general population does predict progression within that longitudinal study. In some of the studies I mentioned, for example, some of those Canadian studies, one of those has longitudinal data on VCDR and IOP over time. And so they are collecting more data. Currently, they just have just 2 time points, and they're only 3 years apart. So it's not enough to show a progression change. Although I'm pretty sure that's just 'cause it's not long enough. I mean, if we hadn't had COVID, we would have more data from that, and longitudinal studies of that size, are clearly going to be very important in terms of training models to be most practically useful.
Same question to Anthony, and also with that sub question, have you looked at serial data sets where you have progression rates over time and tried to correlate it to the information that you're elucidating?
Well, to answer that first, I think we've been underpowered to do that. You've seen what sample sizes we need to make discovery even for glaucoma, yes, no. And so I'm excited about the linkage we're doing with the Medisoft longitudinal data. So it's getting data like those moving dots, that visual field progression data with the genetic data. But a couple caveats here. So one thing, when you look outside of ophthalmology, if you look at cancer, for example, the genetic factors that predispose people to get some types of cancer don't predict which people are going to do badly from that cancer and their ultimate outcome. And that you see that across multiple diseases. So the genetic factors which mean you get the onset of glaucoma might not necessarily be the ones that mean you get bad glaucoma. The second thing to say is all of these cohorts are treated. And so you might be that the person who's at highest risk of progression has a rate of progression of 0 because they've had a trabeculectomy. And how we tease that out is not so straightforward. We have some ideas, and our natural history data sets are pretty small actually. And we've got things like the placebo arm of UK glaucoma treatment study, but in general they're quite small. And how we handle that complex phenotype, because rate of progression is related to untreated IOP, response to treatment, the susceptibility to progression, have they had surgery? It's a complex phenotype of all of those things. So it's not going to be straightforward, but it's something we should definitely look at. And with the larger sample size we'll get with UK Biobank, I think we'll be in a good position to do that.
Yeah, it would be interesting even to use the data that you've collected, the information you collected, to begin looking at even limited data sets. Last question, Stuart, I'm going to ask it to you. The data that's presented using largely GWAS, and I'm wondering, whole genome sequencing is in the air, cost is dropping, and what's the role of whole genome sequencing? What new information are we going to gain with whole genome sequencing?
Yeah, so in terms of the exome sequencing, we're finding a few new things, but not many, because the sample size need to be very large, and yeah, it's pretty clear for most common complex diseases, 500,000 people in UK Biobank is not enough. 10 million is probably not is a reasonable number where you might start finding things. So that's with exome sequencing. Whole genome sequencing is more difficult because you can't prioritize particular variants, so the multiple testing burden is more difficult. So essentially, you're doing a GWAS with slightly better coverage. And everything we know about GWAS so far is that sample size is more important than coverage. So it's, yeah, whole genome sequencing would be better, but it's not going to be dramatically better. It still doesn't change the underlying biology of glaucoma, is that it's a combination of very small effects, small effects on pressure, small effects on retinal thickness, other measurements. So the biological reality is that we need enormous sample sizes to characterize it in terms of finding new drug targets, but also in terms of prediction, which I think is probably the most exciting thing in terms of genetics.
Well, again, thanks so much for bringing all this great information to the group today.
Thank you. I think that there's other questions, but I'll just say briefly as the mic is heading toward the next question is that this is an opportunity, right, to apply this methodology now to longitudinal data sets. And so we need to get funding for that because that's really going to help us to validate whether or not these genetic risk scores or whatever omics mechanism that you apply is going to really predict who the bad actors are, who the people who are going to progress, who we need to really focus in on and get their pressure as low as possible.
Great talks, and I really enjoyed this session. I had a question for Anthony and for Stuart, both. For Anthony, I think that your work from UK Biobank on risk factors has really put into question how much can we trust all the work that was done on risk factors before we had any genetic information? When you start looking at associations of risk factors with an outcome, and if 90% of the population, no matter what you do, are probably not going to get the condition, you're greatly diminishing your chance of finding any association. So all the association may be in those who at least have some susceptibility to the disease. And so, how do we kind of reevaluate that body of work? And going forwards, do we need to think of this in every study that, that looks for risk factors? Because if you're not at risk, you're not going to get it no matter what you do. And I wanted to hear your opinion on that.
Spot on, yes. I think looking at risk or any outcome with glaucoma and not taking into account the genetic predisposition won't make sense. The polygenic risk score is probably already as important as age, and it, as Stuart shows, it just keeps on getting better every few years, and it's going to be the most important thing. So I would say not just for observational studies looking at risk factors, even for trials. So anyone here who's doing anything in humans where you are trialing a new drug, or you're just creating a cohort that you're well characterizing and looking forward, even if you can't afford the genotyping straight away, in your study design and consent, allow for banking a sample and take that sample, because it will be really, hugely useful. Wouldn't it be great to look back at the previous studies of neuroprotection and look at whether maybe a genetic subset of glaucoma actually did have a neuroprotective response, for example. So I think all of the current studies of nicotinamide are genotyping all their participants. So I think more widely, that's my strongest recommendation.
Yeah, I think we probably need to think about, and maybe this is a separate discussion, what is the statistical methodology to understand, well, if you end up getting an outcome, when you have a 1% risk of getting it versus if you have a 12% risk, how do you model this statistically? I'm not sure that the traditional methods are exactly the right way to do it, but maybe they are. Stuart, I had a question for you as well. I was really interested in your comment that the family history didn't seem to give the same information as the genetics, although you would assume that a lot of that is genetic. And I was kind of always, one of the things in the Barbados family history study that always stood out to me is that the spousal risk is about the same as the sibling risk of getting glaucoma. Nobody ever talks about that, but it stands out to me always in the paper. And so then I've always wondered, is a lot of the familial risk, behavioral, environmental? I mean, these people live in the same environment, they eat the same food and everything else. And, is that why you're not seeing an overlap? Or, I wanted to hear your thoughts on that.
Yeah, I'm currently not convinced that the environmental component is in any way significant in the way that you're suggesting. I mean, in terms of when we looked, so we've only just started looking at the family history. I mean, you get differences between different classes of relatives, and as I showed, if you get multiple relatives, then your risk goes up a lot. We've looked at things like whether different types of first-degree relatives are more important in terms of siblings or parents. The effect is larger in siblings, but I think mainly just because of an earlier onset disease. If you have a sibling who's affected, so I don't think it necessarily says anything. Those siblings share 50% of the genes, and parents share 50%, just with different degrees of variability. So most of that just to do with the age of onset, but a model of degree of relatedness does a pretty good prediction. In terms of why that doesn't overlap more with PRS, even though these PRSs we're using are exciting, they still only index a small proportion of the overall genetic risk. And so it's early days, but there's at least some indications for other complex traits that there's more correlations between PRS and family history as the PRS gets stronger. And so I think that's as we'd expect.
Can I make one comment on that? I think all family history estimates are really biased, because once someone's been diagnosed with glaucoma, they only then find out they've got a family history, or they then get their siblings to go who've got a slightly suspicious disc and they get diagnosed, and so on. So the spousal thing, I think that's just, oh, my husband's got glaucoma, I better go and get checked out myself.
Well, not in Barbados. I mean, because they actually evaluated the people. So
right.
In general, yes.
Right. Okay.
But but in Barbados and the Rotterdam studies, I would not make that comment for those studies.
And so in EPIC Norfolk, for example, we've longitudinally looked at people, and when you look at the family history when they were younger at the entrance to the study, and its relation, it doesn't even associate with future glaucoma, and not many people have a family history. I think in a lot of these studies, people find out their family history or develop the family history afterwards. And so I think it's important to not think that this polygenic risk score is not, we're okay just using family history. I think, that's unbiased. And I think that's going to provide a lot of separate and important information.
Yeah, Simon John has a question, but before he does, I just want to comment about all of this. I think that what you've heard this morning is that primary open-angle glaucoma is a prototypical polygenic disease. And I think the fact that having a family history makes the polygenetic risk scores work even better, indicates that we actually need to genotype more people. And we don't need to do whole genome. We could just continue to do GWAS, because you're saying exome sequencing is not adding that much. So we need to do more patients so we can fill in the architecture. We can begin to tease out the environment from the genetics. Simon.
Thank you all. I really enjoyed all the presentations. It's really wonderful to see all the progress that's happening. Doing most of my research in animal models, it constantly makes me wonder how should your efforts and data be informing what we're doing on the animal side? So it makes me ask the question, from all the pathways and genes and variants you're looking at now, is there a particular aspect you think we should focus more on in animals? And related to that, if we were to try to now make the optimal mouse model based on your polygenic risk scores, what 3 or 4 loci or alleles would you think about combining?
So in terms, you've done some of the most elegant work in terms of histopathology in defined animal model systems and understanding what's going on. And Anthony showed that the lymphangiogenesis pathway was critical for even adult onset primary open angle glaucoma. And Simon, you showed that in mice so beautifully years ago. And so what we don't have, again, another gap, is that, we have a gonioscope, we have UBM. These are really blunt instruments for trying to translate this genetic information into why people's eye pressure goes up. And I'll throw this back out. There's something called white light OCT. It's not like ready for prime time, but the resolution's 1 micron. Maybe we need to take people with defined high scores in the lymphangiogenic pathway and apply this technology on them compared to people with low scores and see if we can, empirically see anatomical differences that will inform the disease process. Yeah, so the point would be, so is asking for clarification about this. I'm no expert on white light OCT, but I understand that it's a basic science tool. It's not quite clinically available, but you can apply it in animal models and you get 1 micron resolution. And so you could look at the anterior segment of, let's say, a mouse eye and really see beautiful anatomy. And that might help us, if we can apply it to humans, to understand at a more microscopic level what's going on. So I see you have that quizzical look on your face, but think about this. We have OCT, we take that for granted now. That's a histological cross-section through the retina. We didn't have that 20 years ago. And so we're not thinking about this technology and applying it to the anterior segment of the eye and merging it with an emerging genetic information to learn more about the disease process. That's all I'm saying in general terms. I don't know if I'm answering your question.
I think it may have utility in research as well as possibly in the clinic, but it is structural versus functional possibly, so there'll be more needed than that. Regarding the polygenic risk scores, though, if you were thinking of your top 3 or 4 loci and how they interact, one of the issues in animal models now in the mouse models is some of the penetrances are around 20% or less. You still need large numbers. It's difficult work to do. If we could make an improved humanized animal model, what would be your top 3 or 4 loci to put together? Are there particular alleles, are there particular human alleles you'd want to put together to interact? Or maybe this is a conversation we should have later, but I think it would be fascinating to make those mice.
Yeah, so that's another great area. I don't know if anyone on the panel wants to comment on what would be their favorite genes to translate to animal models.
When you've got such big, powerful results, then I think what's been interesting has been looking at enrichments in pathways. And I want to bring up what I now call the supplementary table 6 problem. I remember sharing with Darryl Overby on a call. I just showed him a supplementary table 6 from a Nature Genetics article looking at these pathways. The lymphangiogenesis one struck me, and because I could read about it. The others I didn't quite understand. And he looked through all and he said, yeah, all of these make sense to me in terms of aqueous outflow biology. The problem is any search that him or his team or his collaborators do here will never bring up supplementary table 6. And we don't understand supplementary table 6. You don't help us write the papers. And so it's meetings like this where potentially we can share those kind of things. And I don't know how we can better share those tables, but I think within those, and then you can look at the genes that are driving those and look within pathways. Otherwise, you can prioritize according to drug targets or other ways. But I think according to the pathways is a way forward.
Yeah, I mean, one other comment I would have on that is just because the disease is so clearly polygenic, there's so many different genes contributing, which means that there's also a diversity of different pathways. And essentially, as we've done bigger GWASs, the first ones, for example, the first ones we did, I did a work on developing methods for trying to tease out those pathways. For things like corneal thickness, we did those 10 years ago. We did a big GWAS for corneal thickness, and you get collagen, you get extracellular matrix. Those things come out pretty clearly, and that was pretty clear. For glaucoma, there's a big, because we're mapping more genes now. It's a more polygenic disease. There's just so many different pathways coming out. It's both good and bad. It's good from the point of view of having plenty of things to explore, but it's hard to say, oh, well, it's going to be just angiogenesis or one or two other ones. It's clearly it's a complex scenario. You can narrow it down, but there's still many pathways which are significant, and so it's difficult in that sense. But
Derek, you had raised your hand. Could we get him a microphone?
Dr. Lee.
Oh, I'm sorry. He had his hand up, and then you can go. Go ahead. Give him. No, he needs a microphone. Yeah. Okay.
Just to follow up on that question, on Simon's question, I'm struck by the correlation between IOP and risk. And so what I'm curious, as someone who also works in animal models, are those loci that fall off that correlation, that are really contributing a susceptibility that is not IOP driven, and what are those alleles that we might be able to build into our animal models? Because all of our animal models, for the most part, are secondary glaucomas. While we crank up the IOP, it'd be great to not have to crank it up as much to perhaps model something more accurately.
I'll give you one. I didn't present it in the interest of time, but we did look at stratifying the glaucoma loci by IOP, by VCDR. We didn't find too much. Well, basically, the ones that are off the line, which don't fit the IOP line, they're all VCDR loci. So some of them are classical, like 6.6, and those loci which clearly have no effect through IOP. But essentially, we didn't find anything which is off the line which wasn't also a VCDR locus. Because we thought, well, the power of finding so many loci, eventually you must be able to find some things which aren't IOP or VCDR. Maybe there's some other things, but we didn't find any so far. So it's.
But VCDR and not IOP, you might think would be a sort of an optic nerve head susceptibility factor. But at ARVO, just a couple months ago, someone did this new sort of GWAS subtract thing where they took the POAG GWAS, subtracted IOP, and everything fell out, bar CDKN2B antisense 1 and 6.6. Those two.
I remember you mentioned that before. I looked afterwards. There's a button. I didn't see the details of that analysis.
It was only from the presentation. They haven't published it yet.
There's a bunch of other VCDR loci which are clearly unrelated to IOP. Obviously some of them are like TMC01 has a big effect on IOP, so you see a downstream effect on VCDR. But there's dozens of loci which only affect VCDR.
I don't know what maybe it was a mistake, or there was something about that technique.
Yeah, I can reconcile my results after you mentioned that on the call we had.
Yeah, so I wanted to actually touch upon that issue of IOP and then what Bob brought up about the structural issues. So on the clinical side, the cup to disc ratio is really important when we look at it. But as Bob was kind of pointing out, you have pseudo cupping, and then you have very tiny discs also. So the OCT has been really helpful, right? Because we read outside the scan circle, and most of us can spend less time paying attention to the morphology of the optic nerve head, right? Because we care about the nerve fiber layer. That's the currency of our vision. So many of these data sets that you're talking about, you pull out the optic nerve head data, right? So you've cleaned it so that really what we're having right now is a huge conversation for the FDA to say we should only look at IOP as a medication for treating glaucoma, right? That's why we're going to have IOP as the only neuroprotectant, because we don't have great evidence for other things. So if you look at one of the key genes is the ATOH7. So that's the master controller, and below that, there are other genes like the BRN3B family, which is with nerve fiber layer density, dendritic outgrowth, and things like that. So they're all part of that same developmental pathway. And so one of the things that's really important to me when I look at the cup to disc is if there's notching, or there's it's not just the circle within a circle, the donut, right? It's actually whether it's a notch somewhere, the morphology of the nerve itself, not just the circle within the circle. So I think that's an important part when you drop out the IOP and you're left with just structural data. What are the structural risks? Because if we're going to look for other things other than IOP to treat, that's an important aspect. And I'll give you an example where you can really look at this in terms of the dogma. So when we train in ophthalmology, we talk about anterior ischemic optic neuropathies, and we always talk about the nerve at risk. What's the nerve at risk? It's the crowded disc. And the crowded disc is a small cup to disc with a tiny, cup, or even a non-existent cup, and they will claim, well, it's so crowded, that's why they have an anterior ischemic optic neuropathy or something like that. So I think you have the data to try to go back to the physiology and to really go back to some of the structural dogma, because it's clearly the IOP is dropping out as a big factor. But now you have this chance to look at some other factors which may be just as important. But it's just that we don't commonly measure it, right? You don't have a great data set to say how many people actually looked at notching in all those optic nerve head photos, for example. So I just thought there was an opportunity there.
Can I just add that for some of the things you talked about, like data that maybe not notching per se, but in OCT reports, and then Dr. Weinreb's comments about the visual fields and being able to look at rate of progression. I think one of the limitations that that the other speakers have mentioned is the fact that we don't have great longitudinal data sets, and in part that is because our vendors have not all adopted data standards and have not made it easy to extract that data out. And so I think as a community, we have to really advocate for that, because if we do want to look at sort of developing these models and risk scores, but also validating them in different populations, we really do need that real world data, and we need to have that data available, which right now it is not routinely available. So if we look at our EHR data, for example, not all places even have structured data for IOP or visual acuity. Increasingly, many of the vendors do have those as structured data, but things like mean deviation or RNFL OCT thickness, those are not routinely available, and because they're sort of stuck in the devices or in the vendor proprietary PAC systems. And so I do think that that is something for the future, as we're talking about all these different things about how we have more appropriate phenotypes or outcomes and the different modeling that we need to do. A big part of that will be, we need that data available, and we need more and more people to tell the vendors to give them that motivation to work on those, so we can have that data.
Thank you for bringing that up. Such an important point. There are over 500 FDA-approved AI algorithms in medicine. The majority of them are in radiology. Why? Because they don't have this DICOM compliance issue. In ophthalmology, we have a handful. We should have like 10 in glaucoma. We don't, because of this DICOM compliance issue. Thank you.
Have it.
So I don't know who's next. I'm sorry. Okay, go ahead.
Great morning, great talks. I have a question to Anthony. The data you showed on IOP and blood pressure was really remarkable. But I think it's taken from one single measurement of IOP, is that correct? And are you surprised, given the variation there is with diurnal, nocturnal changes with blood pressure and intraocular pressure? And what's the meaning of that? Should we be looking, kind of a continuation to a different question by Weinreb, of how, should we be looking at data over time as well?
I think, epidemiologically, the relationship between blood pressure and IOP is really strong, and it's probably much stronger than we're seeing because of what you've said. That my interpretation is, I keep my mind open that an individual's blood pressure may well be having a clinically meaningful impact on their IOP. And just because the between individuals difference, with all the noise that you get in these population studies, the effect size isn't that big. Within an individual, it might. And so when patients ask me, does my blood pressure matter for my eye pressure? I say it probably does, but we don't know by how much.
And do you have data on low blood pressure?
Well, that graph was on the full range, but do you mean on low blood pressure and risk of glaucoma?
With glaucoma, right?
Yeah, I mean, it's so complex, isn't it? And we've got the major confounder of blood pressure treatment, and growing evidence that some of our blood pressure treatments may have influences on glaucoma risk other than via blood pressure as well. So yeah, that's for something that we measure regularly, something that we treat regularly, and that we don't really understand fully its consequences on glaucoma risk. I think that is another area of research priority.
Thank you.
I have a question for the whole panel and anybody else that wants to take this. I was struck again by how strong the associations with intraocular pressure are, and yet the effect is really small. Statistically, it's huge because you have a huge population that you're looking at. But some of the work, for example, on alcohol consumption or caffeine consumption, we're talking about 0.5 millimeter of mercury. This is clinically not significant. So why?
Yeah, let me start. So we're biased by studies that said if I go run 3 miles, my eye pressure is going to decrease. And so we think, therefore, that exercise is something that's going to lower IOP. And to some degree, that's correct. But on a 24/7, 365 level, the effect is small. And it's because these eye pressure measurements are point estimates. And so that's kind of why some of this is happening. I don't know if other people want to comment.
I mean, one comment is, there is this, we need to work out actually as a community, because I'm kind of annoyed at papers being rejected by saying this effect estimate's not clinically meaningful. What, on an observational level, is a clinically meaningful difference in IOP? To put it in context, people who use systemic beta blockers, which we know profoundly lower IOP, and that was the basis for developing eye drop beta blockers for the treatment of glaucoma, one of the mainstays. The difference is around 0.5 millimeter of mercury from users versus non-users. So I would say 0.5 millimeter mercury difference, in that sense, is pointing towards, a major treatment for glaucoma. So I don't think personally, I don't think 0.5 millimeter is insignificant. No, this is systemic beta blockers, tablets, not the eye drops. But exactly, we're watering down what the individual pre and post difference would be. And so I can't tell you what the difference would be within an individual if they went from drinking 100 units a week to 5 units, because we don't have that data, but it's probably more than 0.5 millimeter of mercury.
So we do have an online audience, and so I have a question from the online group, and it's directed to Stuart. How do we reconcile polygenetic nature of glaucoma, drug discovery, and treatment? So many genes involved. Are we going to need many genes to address glaucoma?
Are we going to need many genes to...
Many drugs.
Many drugs. Yeah, so I touched that in my presentation about whether it would only be... So for example, I guess one example case would be that for age-related macular degeneration, there are some treatments which are specific, for example, to someone who has a particular CF5 mutation, and so that targets that particular pathway. So there are some examples where you get a genetic discovery and then you want to treat things in that way. But I think in general, each of those individual loci that we're finding as a potential to pharmaceutically perturb that pathway, and it's just finding out which of those pathways are to prioritize them. That those perturbations can be as big as you want them to be based on how you can modulate those in terms of pharmaceuticals. They don't have to be in someone who carries a particular rare CF5 or other mutation. And so I think, obviously, those will differ on a case-by-case basis in terms of how effectively you can drug that pathway. But in general, I don't think there's a need to... There may be some cases where you can fine-tune treatment to a particular genotype, but in most cases, we're just looking at ways of lowering pressure, potential neuroprotection targets, which would work across a whole range of different people. So I think there's a broad potential as well as a specific potential.
Yeah, I agree entirely. I think, there's an opportunity here to find the axe that breaks the Gordian knot. And an example of this comes from diabetes. So PPAR gamma is a gene associated with type 2 diabetes. The odds ratio for that gene is 1.1. And that has translated into a drug that treats millions of people with diabetes. So it's an exciting opportunity, I believe.
Dieter Reinhardt, McGill University. I'm an extracellular matrix biologist, not working on glaucoma. But what strikes me in terms of pathways is the extracellular matrix. I mean, there's LTBP2 a microfibril-associated protein, collagen 5, the alpha-2 chain, collagen chain, FKBP9, collagen modifying, a folding type of gene, laminin B2, basement membrane gene, integrin beta-3, that binds all of this to the cell. So this is really kind of sticking out to me, extracellular matrix pathway, and Stuart, you mentioned that briefly already. But are there some ideas how this pathway could be affected really in Schlemm's canal, or perhaps around the optic nerve, or not sure.
I'm not sure I have a good answer for you. We have tried to tease out the effects of, so I guess there was a concern that, so some of the early studies that we found for corneal thickness, we found extracellular matrix coming out, and we found that when we've corrected for those, there's an artifact there in terms of measurement of intraocular pressure. And so I guess things have gone up and down in terms of the how much stock we put in extracellular matrix in terms of the contribution to glaucoma. So I guess there's, so it does come out as a strong pathway in the initial glaucoma GWASs, but when you correct for, use corneal corrected intraocular pressure, those go away. And so, based on that, it's hard to say, but also I guess I'm not working in that particular space, and so I know a lot less than you do in terms of how we might harness that going forward.
Okay, thanks.
It's certainly not turning up as a prominent pathway for POAG or IOP. That's what the data is saying. A lot of these are related to endothelial cells, a lot of the genes that we're finding.
That was a series of great talks. I feel like I personally learned a lot, actually. So I'm wondering, this is a fair question, but given what you guys have found regarding risk factors, from a clinical perspective, for the benefit of our patients, for those of us who are clinicians, what is a fair summary of what we can tell our patients when it comes to risk factors? Should we be telling the patients with the multiple first-degree relatives with glaucoma to cut out all alcohol, to cut out all caffeine, to make sure their cholesterols are controlled? What is a fair 1 to 2 sentence summary that we can tell our patients?
So I would say that what we've learned is that if you have probably two relatives, sibs or mother or father, with glaucoma, bona fide primary open-angle glaucoma, that's probably going to be pretty equivalent to being in the top 25%, maybe top 10% risk of having POAG. And so everybody in that family needs to be evaluated. And I do believe that the caffeine data that Anthony showed is pretty impressive. And so, those people are consuming 4 plus 5 cups of coffee a day. They probably should, if they have 2 relatives with glaucoma and they're drinking 5 cups, they should probably cut down to 2.
So I'm not sure anytime soon we're going to get a prospective intervention study, maybe something about alcohol reduction or caffeine reduction or some kind of glaucoma healthy behavior study. Maybe we'll get that in the future. Until then, this might well be the best data we have. And I think we need to be able to communicate that to our patients along with the uncertainty that's around it. And there's stuff in the newspapers every day, isn't there, about some kind of lifestyle and some kind of human disease. We don't have to limit this to just people with a family history. People who are doing 23andMe now, they're getting their polygenic risk score for glaucoma. There are going to be members of the public who are receiving this information already. Interestingly, their recommendations are a little bit odd. They say stuff like, make sure you wear goggles when doing DIY, but they do say limit caffeine consumption. So that's interesting. So, I would tell people, well, there's some evidence about alcohol, some evidence about caffeine. For other patients where we don't even know their genetic risk, but let's say a mild glaucoma patient in my clinic who's stable, I don't bring it up unless they mention and say, is there anything? I'll say, well, there's this evidence. It's not really looking at glaucoma progression, but that's what we know, so that they at least have that information. If it's somebody who's getting worse despite my best efforts to treat them, then I bring it up anyway, even if they don't ask, because you're desperate in that situation.
So we're at 10 o'clock, and I want to thank all of the speakers for just world-class talks, and what a great discussion, what a great way to start the meeting. We're going to have a break now, and we'll reconvene at 10:15.
Can I ask one question first? I'll make it quick, although the answer may not be quick. I think you guys have all made very elegant arguments why we need standardized care, we need standardized data acquisition, and the UK database is great. But you've also made the point that we need more patients. So with the available resources, are we better off getting more patients in this very standardized way? Well, the alternative, because there are many centers around who, you mentioned Epic, everyone puts that in differently, but given that DNA sequencing is so relatively cheap now compared to patient characterization, are we better off putting the resources to get a lot more patients, even though the data about them is noisier? So between having very well-characterized patients and trouble getting them, or less well-characterized but much bigger numbers, which is a better use of resources?
Stuart, want to take that?
I mean, it's as you mentioned, genetic data is ever cheaper to collect, and so it's really the cost of having well-curated clinical phenotypes. For me, having a large-scale longitudinal study would be extremely useful, because that's one of the big limitations we have in terms of things like developing models for progression.
Yeah, I would say we need both, and the evidence so far is showing that both works, right? Because in Stuart's paper, you've got UK Biobank, where people at least have had IOP in a standardized way, and then you've got 23andMe, where someone says, yeah, I got glaucoma. And we're learning more as we just, lots of messy data and lots of organized data is moving the field forward. Well, you know, what's happening is like at Mount Sinai, we have something evolving called Mount Sinai Million. We're going to genotype 1 million people in our healthcare system. And I think you're going to see more healthcare systems doing that. Unfortunately, that's messy data. But anyway, you wanted to say something.
Yeah, I was going to say we have, I think there are ways to leverage ongoing efforts as well. Like the Odyssey organization already does a lot of standardization, and many institutions have invested in OMOP, a common data model, data marts. And so that infrastructure already exists. Most of them do not include ophthalmology data for the reasons that we talked about, in the lack of standardization, the lack of standards compliance. So I think that will be part of it, is as we develop those standards, then to be able to leverage that existing infrastructure so that the incremental cost of developing sort of like distributed data networks will be less than if you were trying to create them de novo.
We need to take a break at this point. Thank you.
Sorry you didn't give me a talk.